Hello, my name is Kelsey Gersheim. I'm a PhD student at the University of Illinois in Champaign-Urbana. Today I'll be talking about the main project for my master's degree, which was to ask a fairly simple question, which was how efficient are fall applications of anhydrous ammonia, specifically in the Midwest. You'll see some important people at the bottom of the slide. My advisor, Dr. Richard Mulvaney. Shout out to him for being patient with me during this whole process. Also shout out to Tim Smith over at Crop Smith from Farmer City, who's a very important person in this project and honestly in a lot of other projects we're working on. And then the two statisticians that were helping us for this project, Shelby Henning over at Midwestern and Alan Hertzberger here at UIUC. So for those of you who aren't aware, this type of application is fairly common in the Midwest. About 50% of all of our nitrogen goes on as anhydrous, and then about 50% of that anhydrous goes on in the fall, the other half being applied in the spring. And there's some obvious fluctuations in this value. You can imagine that 2019 is going to be one of those fluctuations. However, this is still a very popular choice among producers, right? And there's a reason for this. This type of application allows the producers to apply before the busy springtime. There's also often better soil conditions when we think about things like getting equipment in and out of the field, reducing the risk of soil compaction, all important factors. There's also the incentive from the fertilizer companies to spread the infrastructure over the course of the year. But despite all of these kind of benefits of this type of application, there's one very large downside, and that is that with this application, we're putting the nitrogen out there a good 6 months prior to crop and uptake. And during this time, we can have loss. Soil microbial activity persists, and that can be a problem. So one solution to this problem has been to include a nitrification inhibitor. You'll see that I have N-Serve here on the slide. The reason being that N-Serve just is the most common nitrification inhibitor used. You might hear me call it nitropyrin or see it on the slides. Just know that nitropyrin is the chemical name for N-Serve. So nitropyrin and N-Serve are the same exact thing. Why would we want to add these nitrification inhibitors, or how do they work? Well, they inhibit the oxidation, or even more specifically, the microbial oxidation of ammonia into nitrate. When we have nitrate in the soil, it's very easily lost in comparison to ammonia that can be lost by nitrate leaching, it can be lost by denitrification. So the idea is that if we can stop this conversion, we will reduce the loss. So, this has been a practice that's been around for a long time, and N-Serve is such a popular additive to this type of management that we decided to include it in our study. We weren't wanting to do a realistic evaluation, and because so many producers use N-Serve, we wanted to include it. And kind of just to get everyone in the same mindset, how did we want to evaluate this practice? There's lots of different ways we can look at a practice. And we wanted to look at it in terms of efficiency. So just so we're all on the same page, when I say efficiency, I mean the fertilizer nitrogen uptake efficiency. So of the nitrogen that we apply, what % of it is getting into the crop? Very important question. And it's important for a couple of reasons. First, as a producer, we want to know, right? So ideally, we would get the most of our input into the crop. But it's also important when we think about environmental impacts. Because if we're getting the most of our input into the crop, that means we're getting less of it into the environment. So a high efficiency is really a win-win situation. You can see the equation here on the slide. It's simply the crop uptake of nitrogen divided by how much we apply and multiplied by 100. So just as an example, if we apply 100 pounds, and let's say 50 of those pounds gets into the crop, that's a 50% efficiency. So the holdup kind of is that there's multiple, I guess maybe there's only two different ways we can measure efficiency. Two main ways, I guess. And the first, and by far the most common, is something called the difference method. It's very easy to understand. we have a plot that is fertilized, we have a plot that is not fertilized, and we take the difference to understand the gain in yield from the fertilizer, right? So in this example, we have a plot that's been applied with 100 pounds. So if you can imagine, this plot is including the soil nitrogen and as well as the fertilizer nitrogen. Then we have this plot over here that's just the soil nitrogen, right? There's no fertilizer added. If you take fertilizer plus soil minus soil, you get fertilizer. So we can take that value, excuse me, divide it by the N applied, in this case 100 pounds, and we can get the percent of uptake efficiency. Super easy, right? Easy peasy. Well, there's a problem with this type of estimation of efficiency, and that's that there's no clear distinction between the soil N and the fertilizer N, which is a problem, right? We're trying to understand the efficiency of one of the sources, and with this type of estimation, we're not even making the distinction between the two sources. That brings me to the technique that we used in our study to measure efficiency, and that is N15. So for those of you who don't know, N15 is a stable heavy isotope, which means it has an extra neutron than what's found in the majority of nature. And what we can do is we can use this as a tracer. Some people call it labeled in nitrogen, some people call it tagged. It's basically a tracer, and we can enrich a nitrogenous fertilizer source, whether it's urea, UAN, whatever, anhydrous ammonia. We can apply it just like the producers would, and then we can trace where it goes in the plant or even in the soil if we want to. So you might be thinking, well, this is great. We have this practice we use a lot. We have this technique that honestly has been around for quite a while. Why haven't we seen data using this technique? Because I'll tell you right now that what I'm presenting to you right now is the only study to use labeled anhydrous ammonia to evaluate fall applications. Well, there's two reasons why. They're both pretty easy to understand. The first is cost. So you're going to, think in your mind how much 100 pounds of N is anhydrous costs. Just fertilizer grade anhydrous. Well, compare that to the cost of N15. If we were to buy 100 pounds of N as labeled anhydrous ammonia, it would cost $86,046.76. Pretty pricey. And again, that's just the cost of the material. That's not including the analysis, all the labor that is involved, which I'll talk about a little bit later in these types of studies. So very, very expensive. The second, which a lot of people are familiar with, especially producers, is handling anhydrous ammonia, right? It's a pain in the butt to handle. It's a toxic liquefied gas, very dangerous. Because we have these expensive prices for N15, we have to use small plots, right? We can't afford to apply acres and acres of N15. So again, if you think about applications with anhydrous ammonia and think about how you would do that with a small plot, it becomes challenging. And the third, really, we imposed on ourselves, to be honest, and that was that we wanted to make sure that the applications we were doing were realistic or in keeping with what producers are actually doing. We didn't want to go out with our lab coats and syringes and apply the ammonia. We wanted to make sure that we were doing it in a way that was similar to how, conventional practices would be done. So before we could even really start this project, there was a lot of groundwork that needed to be laid out. And if you're interested in the details of this, I would just point you in the direction of the paper highlighted at the bottom of this slide. And what this paper is doing is talking about, or I guess even describing, three parts of the system that we designed to do these types of applications. The first is we have to generate the ammonia, we have to make the ammonia, and that was accomplished by the manifold that you see in the upper left corner of the slide. The second was we have to house the ammonia, right? We have to have something to keep it in. And the third was, how do we apply the ammonia? You'll see the toolbar modified by Tim Smith over on the right. So just to go through these briefly, first, the manifold system. So generating the ammonia, how did we accomplish this? you'll see the schematic on the slide, and basically what we were doing with this manifold system was cryogenically transferring known amounts of labeled and unlabeled into the collection tank. So on the right hand of the manifold, you'll see the source cylinder, and there's really two parts of this manifold. The first part up here is the portion that was used for the labeled ammonia, or the enriched ammonia, the N15. So you'll see we have an expansion tank, and really the purpose of that expansion tank, we didn't want to make a whole bunch of tiny transfers. We wanted to transfer large volumes at a time. Large volume equals large mass, right? So the expansion tank was just giving us the volume that we needed to move larger amounts, I guess, at a time. You'll notice that the second half of the manifold looks very similar to the first half. It's just the proportions are a little bit different. So expansion tank 1 was about 20 liters. Expansion tank 2, affectionately named Big Bertha, could hold about 800 liters. The reason why we have these two different sizes was because when you go to buy N15, you buy it at a very high enrichment. It's about 99%, and we needed to have about 1 to 2% N15. So what ends up happening is you need a very small quantity of the N15 and you need a very large quantity of the unenriched or unlabeled N15. So at the end of this process, we have a collection tank that has labeled and unlabeled N15 at a concentration that we want. And it's been frozen into this collection tank using liquid nitrogen. So that brings us to the collection tank. So how do we house this thing? Well, the collection tank had a 3 kilogram capacity of 6.5 to 6.7 pound capacity. Really, it was just air receiver is all it was. But it had to fulfill a couple prerequisites. The first being that it needed to be leak-free at negative 328 degrees Fahrenheit. So liquid nitrogen is negative 328 degrees Fahrenheit, so we had to be able to submerge these guys without having them, bust open in the lab. We also needed an inlet and outlet, which was provided by TV1 and TV3. The purpose behind those will become more apparent as I talk about the toolbar. We also needed a way to add a nitrification inhibitor. So ammonia can withstand negative 328, but a nitrification inhibitor cannot. So we had to have some way of introducing that nitrification inhibitor after the ammonia had come to room temperature, and that's what the sidearm allowed us to do on the left there. And then, excuse me, maybe a more obvious prerequisite is it had to be able to marry to both the manifold system and the toolbar, which in fact it did. That brings me to the toolbar. So pictured on the right, schematic on the left, you'll see maybe the reason why we have the inlet and outlet now. There's an N2 cylinder mounted on the toolbar, and this was to allow us to keep a headspace on that ammonia. If you think about it, if we're out in the field being jostled around, this isn't a big tank, right? So it's a pretty small quantity of ammonia. We were concerned about things like sputtering and inconsistent flow. So keeping that headspace on that collection tank was kind of a attempt to keep the flow consistent. You'll see we also had a flow regulator, hydraulic actuator for Tim the cab, and a distributor. So we have this system, but obviously, you want to make sure things work. So we did an evaluation of this toolbar system, and the first evaluation is one that I'm sure most of you are at least familiar with, which is called bucket testing. So it works off the principle that ammonia is hydrophilic. It loves water, right? So we can dispense ammonia into buckets of water. We can measure the weight gain in the bucket, and we can time the dispense, and then we can calculate flow. Now, water is a little bit different than soil, and the bucket testing is done stationary, so we wanted to do a little bit more of a robust evaluation. We thought, well, we have this N15, there's some soil outside, why don't we just go outside and apply it into the ground and measure how much we have, right? that's exactly what we did. We wanted to look along the band, so are we getting consistent flow along the band as well as among the knives. So to do our sampling, we have this kind of cool probe here, the Gideon's probe. I think it belonged to BASF. But basically, we were able to take slices out of the band. And again, like I said, look at along the band and among the knives. So once we had done this, we were, confident in the data we were getting, and we wanted to go ahead and move forward with our application. So here's a picture of the toolbar kind of in action. You'll see Tim in the cab and Dr. Mulvaney on the side. Again, small plot research. So more about the trial. Let's talk about data. How efficient is fall applied anhydrous? Well, we had 2 years we were looking at, 17 and 18, the growing seasons of 17 and 18. So we applied in the fall of 16 and 17. And in each of those years, we had 3 sites. 2 of the sites were mollisols. Mollisols are soils formed under prairie, so they're richer soils. They have a higher fertility. And one of those was a corn-soybean rotation, the sable, and then the Elburn was continuous corn. The third site was an alpha-sol. Alpha-sols are forested soils, and they're poorer. They have lower fertility. And that one was a corn-soybean rotation. So at each of these years, each of these sites, we have these 3 treatments here, 200 pounds of N per acre as labeled anhydrous minus NP, that's without N-serve or without nitropyrin. We have the same form and rate for our second treatment, but this time with nitropyrin or with N-serve. For our last treatment, we had an untreated check, so a plot where we didn't apply anything. And we didn't need that plot to measure efficiency with N15. But you'll remember at the beginning of this video that I talked about the 2 different ways of estimating efficiency, by the difference method and by the isotopic method. So the difference method can be calculated using this untreated check. So we included it because we wanted to compare, what is the difference between the difference method and the isotopic method of efficiency, right? So at each of these, in each of these years, each of these sites, each of these treatments, we had 3 applications, and you'll see on the right kind of the dimensions of our plot. Again, small plot, 10 feet by 7.5 feet with ample border. The border is important when we think about things like lateral movement of N15 as well as lateral root growth of the corn plants. So once this was applied, waited till harvest, and at harvest we did everything by hand. We separated the plant parts into grain, leaves, stalks, and husks. We wanted to look at those separately. I just want to point out that the roots are not involved in this, so an important note. Everything was dried down and stored appropriately. So now we begin the processing of the samples. So how do we deal with these samples? What do you do with them? Well, first we have to process them by grinding them down. So we used fairly simple pieces of equipment to do this. The first being a KitchenAid, actually, with a mill attachment. The second being a Wiley mill. Both of these have the advantage of being able to open them up. You could open the face of them up, which is really important because we had to clean meticulously between each of these samples. So myself, Mulvaney, Vander, one of our postdocs, and a whole bunch of our undergrads would literally clean these pieces of equipment out with dentistry tools, methanol, and water. So a lot of care has to be taken for these types of samples. Again, maybe why we don't see a lot of studies done with them. After everything was ground down, we determined total nitrogen using Keldol digestion followed by mason jar diffusion using sodium hydroxide as the base. So what this is doing is we're just trying to figure out the concentration of nitrogen in the plant. So we haven't even touched the N15 part of it, just how much nitrogen is in these plant parts. After that's done, then we can start thinking about N15. So we use something called a mass spectrometer to measure the ratio of N15 versus N14. And this is the mass spectrometer that is used in our lab. Mulvaney's been working with this piece of equipment for a while now, and he's it's his baby. He knows it very, very well, and it's able to put out a lot of data. So at the end of this, really we have three important parameters, and those are we have the dry matter, or the weights of everything. We have the concentration of everything, the concentration of N of everything, and we have the source of where that nitrogen came from, i.e. N15, right? So there's a couple of parameters that we can calculate using these three measurements. But before we get into that, I want to talk a little bit about the sites. So in this graph, you can see I have the 6 sites here, and something that's super important about the setup of this project is that we had this same 3 soil series each year, but we had 6 separate locations. Very, very important. 6 separate locations, okay? They were not the same sites. Which is kind of confusing because we did have the same soil series. So in some cases, the 2 Birkbecks, I believe, were, a couple miles apart. So they're not the same site. What this graph is showing is organic carbon and potentially mineralizable nitrogen, organic carbon being in gray, potentially mineralizable nitrogen being in red. These are just fertility measurements, okay? So the more organic carbon, the more potentially mineralizable, and the higher fertility of that site. And I want to point out a really important difference between the 2 Birkbeck sites, because it kind of shows up in the data as a trend pretty consistently. You'll notice that Birkbeck in 2017, or site 2, was a lot higher in fertility than the Birkbeck site 5 in 2018. There's actually a reason for this. The reason is that site 2 had been previously pasture up until about 1992. So, you can kind of see the legacy of that pasture in that fertility. It's got a higher fertility because of that. Now, in contrast, if we look at Birkbeck site 5, that's a lot more lower in fertility. This site has been continuously cultivated for 70 years. So it's been depleted, low fertility. That soil is not getting as much as the soil from the Birkbeck site 2. So let's first look at dry matter production. This is probably data that you guys have seen before or are used to seeing. The first thing that I'd like to talk about is response. So when I say response, I mean the difference between when we do add nitrogen versus when there wasn't nitrogen added. So I have the sites, I have the treatments. You'll see minus NP or minus Nserv, no Nserv, and then plus NP or with Nserv, and then the last being the untreated check or the plot with no nitrogen. So when I say response, I mean that the untreated check was significantly significantly lower than the 2 treatments above, which had the 200 pounds of N. Okay, so looking at these 6 sites, there were actually only 4 sites that were responsive to N, or there were only 4 sites that saw a significant increase in yield when nitrogen was added. Those sites were site 3, 4, 5, and 6. For those of you who care, the N response at these 4 sites range from 24 to 83%, 53% on average. So, that kind of makes sense, and I think, producers hope that would happen, that if you, add nitrogen, you would have an increase in your yield. So what happened at site 1 and 2? Why didn't we see a significant increase in nitrogen when we added, significant increase in yields when we added nitrogen? Well, at site 1, stable, that site was so high in fertility that it didn't need any nitrogen. The native N supply from the soil was high enough that it didn't matter if you added nitrogen because there was already so much there that you didn't get an increase in yield. Site 2 is a little bit more perplexing. If you look at the untreated check, you'll notice that it's 140. Visually, it looks like there's a huge difference between 159, 174, and then the 140, right? So why isn't this significant statistically? Well, it's because it was previously pasture. This is a trend that we saw in a project that we did a couple of years ago. If you're coming out of a pasture, that makes the variability in nitrogen supply fairly large. And what happened basically at this site was we had so much variability in nitrogen spatially that it just dwarfed the treatment effects. So now looking at all the sites again together, now we can look at with and without N-serve, right? So now forgetting about the untreated check, just looking at with and without N-serve. Was there a difference when we added N-serve? Did it help the yield or did it not help the yield? We actually only had one site that was significantly different when N-serve was added. So for 5 of the sites, it didn't matter if you added N-serve, you got the same yield. The site where this happened was actually site 6. So the only significant effect of N-serve was seen at site 6, and lo and behold, it's a decrease. So the only significant effect of N-serve at our site was a decrease in yield, which is interesting. This isn't a new finding. Touchen et al. Found this same thing in 1979, or I guess in a publication in 1979. And they too saw it on a continuous corn site, just like we did, which kind of gives you an idea as to why you saw a decrease with N-serve. So if we think back to what N-serve is doing, it's keeping that nitrogen in the ammonium form. Microbes love ammonium, okay? And if you have ammonium and you have all that carbon, you're going to promote immobilization. Immobilization just means the microbes are taking that nitrogen into their biomass and holding it up so the crop can't use it, okay? So that could give us insights into why we saw that decrease there. We'll have a lot more insights on that when we go to analyze the soil from this project, but right now we just have the plant data. So now let's get to the data that's exciting, right? The stuff that we haven't really seen before, which is the efficiency data. Again, just to review, this is the fertilizer nitrogen uptake efficiency. So this is of what we applied. So of the 200 pounds, what percent of that got into the crop? This is the 2017 data. I'm just going to summarize real quickly. For the grain, which we see in the red, it ranged from 18 to 24% efficiency. So that means of the 200 pounds, 18 to 24% got into the grain. For the total, we saw 28 to 32%, which is in the gray. I want to point out again, too, that, you know, the grain is part of the total. It's not like you add these together. The gray is as much as it gets. So these values are fairly low if you think about it. I mean, if you're applying 200 pounds and at the most 32% is getting into the crop, that's pretty shocking. And you know, something that should be considered when we're choosing this practice. There was never a significant increase due to the addition of nitropyrin in 2017. So you'll see I have the negative nitropyrin plus nitropyrin, and there was never a significant increase. Here's 2018, and again, just to summarize, for the grain we had 12 to 33%. For the total, we had 16 to 42%. Again, pretty shocking numbers. That 12% is really scary, and then the total of 16. So there was a site where 16% of the nitrogen was what we got, which is, again, pretty shocking. Birkbeck kind of sticks out with a sore thumb, site 5, and Birkbeck was also the only site where we saw a significant increase in FNUE due to the addition of INSERV. So why is Birkbeck sticking out? Well, again, we can go back to the fertility parameters that I showed you earlier. So if you have a site that is low in fertility and you apply fertilizer, that is going to be more efficient because there is less native nitrogen there, so more of the fertilizer is going to get into the crop. We saw this trend throughout the data, and we can even think about it on the other end of the scale. So the Birkbeck would be an example of on the lower end of this graph, or more towards the left. So you have a low IS&T value. That means that you had a high efficiency. And if we had a high IS&T value, that means we had a low efficiency. So what does this mean? So what is IS&T? I should explain that first. IS&T is the Illinois Soil Nitrogen Test. It was a test developed by Dr. Mulvaney and Saeed Khan. And really what it's doing is measuring potentially mineralizable nitrogen. Even more simply put, it's measuring the ability of the soil to provide nitrogen. How much is the soil providing? Which is a very key concept. And again, it kind of makes sense that you'd see this relationship, right? If you have a site that is high in fertility, there's already enough nitrogen there. By adding fertilizer, you're not helping anything. You're simply diluting your fertilizer, in effect. And then again, on the other side, so the Birkbeck side, if you have a lower fertility site, then that input is going to go a lot farther because the soil is providing less and the crop is more dependent on the fertilizer, and it's more of it is getting into the crop. So in research, we like to compare to what other people have gotten in the past and reflect on things that we can learn about from the literature. And when I started this slide, the title started as comparison from previous studies, but I had to quickly change it to comparison to the only previous study because there is only one other study we can compare it to. So like I said, this is the only project, or I'm sorry, the only study done looking at labeled anhydrous ammonia for fall applications. There was one other study done using labeled anhydrous, and this was to evaluate spring applications. It was done over in Iowa by Sanchez and Blackmer in a paper published in 1988. They luckily were looking at the same rate. Again, they were looking at spring, we were looking at fall. And they didn't ever actually report FNUE, but they reported all of the parameters needed to calculate it. So we went ahead and calculated it. And just looking here, they got 13 to 20% in the grain, 26 to 43 in the total. So comparing that to the values we got, which I put on the right-hand side of this slide, well, there's not that big of a difference, right? 13 to 20% versus 12 to 34%. You know, that's pretty similar. 26 to 43, 16 to 42, not very different. So looking at this, spring versus fall, the same values, you would think, well, it doesn't matter when we apply it. It doesn't matter if you apply it in the spring or fall. You're going to get the same efficiency. So why not just apply it in the fall, right? Well, there's one factor that needs to be brought up, and that's the factor that I've been harping on for the past couple of slides, and that is fertility matters. We look at the organic matter contents of their sites versus our sites, and you'll notice a fairly large difference. They were working on sites that were ranging from 50 to 70 grams per kilogram of organic matter, and we were working on much lower fertility sites, 20 to 45. So if you buy this whole idea of, higher efficiencies mean lower fertility sites, then you take into account that they, in effect, depressed their efficiencies by using such rich soils, then fall applied actually is less efficient than spring applied because we were on lower fertility soils. So before I wrap up, I just want to go over one last parameter. And this parameter is not an efficiency parameter, but it's still very interesting and kind of shows an interesting point. And this parameter is called NDFF, or NDFS. It's the nitrogen derived from the fertilizer, so NDFF, nitrogen derived from the soil, NDFS. So conceptually what this value is if we were to take all the nitrogen in the corn crop, it's what percent came from the soil and what percent came from the fertilizer. So again, not an efficiency value, just showing us where the nitrogen is coming from in a single corn crop. Here's the data here. Quickly, I have the 6 sites on the bottom with our treatments and our rotations. The red represents the percent that came from the soil, and the gray represents the percent that came from the fertilizer. You'll notice again that Birkbeck is kind of the one sticking out. For Birkbeck, it was, again, a lower fertility site, so it's more dependent on the fertilizer, which is why there's a higher percent of fertilizer in comparison to the others. The important point that I wanted to note is that the soil is always the dominant source, right? The soil is always over 50%. And that's an important concept to understand. The fertilizer, it didn't matter, what year, what treatment, what site, the soil was always the dominant source. And this is a trend that's been seen in other N15 studies as well. So to conclude, or maybe even to summarize, NDFF never exceeded 46% in any plant part. In other words, the soil was always the dominant source of nitrogen for the crop. FNUE by N15 recovery averaged from 21% in the grain and 28% in the total above ground biomass. That's averaged between the 2 years. And then at only one of the 6 sites studied was NP significantly effective for increasing efficiency, and that was, of course, Birkbeck, Site 5 in 2018. So just to kind of wrap up and talk a little bit about where we're headed, we have a couple projects going on. One of them is part 2 of the project that I just described to you, and that is to look at the soil. So we also took soil samples during this project, and we're interested in understanding where the nitrogen went throughout the soil system. So we're looking at different depths, different sampling times in relation to the application, as well as looking at different fractions of N. So we're looking at exchangeable ammonium, non-exchangeable ammonium, we're looking at nitrate, hydrolyzable, lots of different fractions to really understand what's happening with these applications in the ground. And then we also have 2 other trials that are using N15. This time we're working with UAN, urea ammonium nitrate. A lot easier than anhydrous. And these are looking at, one of the trials is looking at citrus applications. The other is looking at pre-plant applications. So, we looked at anhydrous in the fall, obviously not the most efficient. So in these next trials, we're hoping to kind of get a better grasp on, okay, what is efficient? What does work? So that's kind of where we're headed. And I'll just share my email with you. I thank you for, engaging in this video with me and listening to the research that we've been doing. And I would be very grateful to get emails from anyone who has questions about the research we're doing, or even just someone who would be interested in having a discussion about, what we've been finding and where we're going.